Hey folks, welcome back to the channel, and in a previous video we talked about all of the simulations I've been running as part of my master's project. If you want to see all that in detail, then watch my last video about my master's project, but to sum it up, I've been running really large-scale three-dimensional fluid simulations of forming triple star systems. I've been looking at how they accrete mass, that is how they scoop up all of this gas out of a disk around them. And these simulations, they've been producing masses of data. Over the last few months, I've generated on the order of a terabyte of data as part of my project, and not much of it currently makes sense, as you can see from, this graph from the last video. Yeah, there's something wrong. How am I dealing with all of this? How am I processing this data? In short, I'm using Python because it is a brilliant tool for the job. If you don't know what Python is a programming language. It's really well designed for things like this sort of data analysis work. Now, some of the stuff that I'm doing is very iterative, so could be better served by a low-level code like Fortran, which I am familiar with. It's actually what the simulation is written in, but Python is just brilliant for everything start to finish. For reading in the data, doing that initial testing, and then actually visualizing the results. There is a wonderfully developed package for Python called matplotlib, and that's what I've been using. And I appreciate that is not really video worthy to say I'm using matplotlib. What is video worthy is to say that I'm using Python to run a Gaussian smoothing algorithm to try and turn this plot into this plot. You'll notice those are very different. What is a Gaussian smoothing algorithm and why does it do that? Now, you might be familiar with a moving average from all the press briefings during the COVID-19 pandemic. This would normally have been mentioned as like a 7-day average or a 5-day average or a 2-week moving average, something along those lines. And essentially what it does is it runs an average over a period of time or a period in the data. So you're not taking an average over the entire data set, you're getting an average over a useful subset of it to see how it compares to different other points in the data set. And that is essentially what I'm running here, but I don't have a hard cutoff. And this is where the Gaussian weighting comes in. A Gaussian is essentially just a distribution. It looks like this. It's sometimes called a normal distribution. So it's a symmetric distribution around a mean point. Now, if you're looking for the Gaussian weighted average around a given point in time, you're going to take an average on the data points around that time, and the ones closest to it are going to be given a higher weighting than the values further away. This gives you a much smoother average overall. You can see how things vary over time as opposed to just seeing chunks of data that are less smooth. This Gaussian smoothing has a characteristic time, so the amount of time that we're actually interested in trying to smooth over. So basically, it will take an average that will pretty heavily weight everything within, say, a 36-year period, but anything further than that is much less. This width is known as the full width at half maximum. On your Gaussian distribution, if you go to half of its maximum height, the width at that point, so there's obviously 2 points at the half height, the width between them in time will be 36 years in my analysis, and I'll come on to why. So why am I doing this rather than, say, just splitting up into chunks and averaging over that? This preserves the quality of the data. If I was going to take the full length of my simulation, all 1800 years, and split it up into, say, 100-year chunks, I could do that, but it would mean that I'd only have 18 data points throughout my entire simulation. Instead of having a nice smooth curve at the end of it, I would instead have basically chunks with straight lines in between them. It wouldn't actually be that useful. You wouldn't really see how they'd vary. There could be a lot more complex information happening there that you're just not seeing. And I don't just mean the wiggles. The wiggles are real, but we'll come on to them. So what has all this processing found? We've established this is a good way to turn wiggly data into smooth data. What have I actually found from all this? Well, I found what I was looking for. I found trends in the mass accretion. So to remind you of what my project is, what the question is I'm trying to answer, what I'm trying to do is to look at how changing the mass ratio between different stars in a triple system, that is a system of 3 stars, affects how it accretes mass and angular momentum. So from this information that I've been able to glean through this data processing, I've been able to find trends. So what are these trends? What have I actually found? Well, what I've found is that our understanding of binary systems can be applied qualitatively, if not quantitatively, to triple systems. So in binary systems, we expect that the smaller star in the system is going to accrete more of the mass. The reason this happens, the reason the smaller star gets most of the mass, is due to how binary stars orbit. Regardless of mass, they don't just orbit a central point where they're both equidistant. Their relation to that point depends on their mass, because that point is known as the center of mass. If you have two stars, one smaller than the other, the heavier star is going to be closer to that center of mass point in the middle, and the smaller star will orbit much further out, much closer to the accretion disk. This means it will be able to scoop up a lot more mass, trending towards this mass equalization. This is what we're seeing in our triple systems as well. We see it for both characteristic mass ratios. First, there's the wide binary mass ratio. This is the ratio between our small binary and our single star. As we decrease Q1, the wide binary mass ratio, we find that the secondary component, in this case our small binary, accretes more mass, accretes preferentially. This is what we would see in a binary system as well. We also see the same thing for Q2, our small binary mass ratio. We see that as we decrease Q2, the secondary component increases its accretion rate. It accretes preferentially. We see the same trends in triple systems that we do for binaries, specifically in hierarchical triple systems, which we try to treat as nested binary systems. This would suggest that this assessment of running them as nested binary systems is a pretty good approximation to what a hierarchical triple is, which is great. Ultimately, this is a good result, and it's a result that hadn't really been found before. So I'm really happy with this. So, have I found anything else? Yes, but there's not really time to go into all of that today. In the next video, I will talk a bit more about some of the results that I haven't had time to talk about in this video. They're kind of weird and they're kind of cool. And I will also be talking about how I've been assessed for this project. And yes, that is past tense. I am now finished. I'm graduating next month, but I wanted to finish off these videos for you. So I'll be talking about writing up the report, giving the Viva presentation, answering all the questions that I had to answer. And if you have questions on this research project, then please do give me a shout in the comments below and I'll try and answer them as well. Thank you all for watching. Please like, comment, subscribe, and I will see you all in the next one. See ya.